In this video, we'll take a look at notes on section 9.1, solving trigonometric equations with identities. So what are trigonometric identities? So we've worked with them so far in the trigonometry section. They're equalities that involve trigonometric functions and are true for every value of the occurring variables for which both sides of the equality are defined. So some of the trigonometric identities you've already worked with are the Pythagorean identities. Remember that the cosine squared plus sine squared of an angle is equal to 1. And where did we get that? We got that from the unit circle. If we drew the reference angle and a right triangle, the y value is the sine, the x value is the cosine, and the hypotenuse is 1. So if we write this right triangle side length relationship in terms of Pythagorean theorem, then the cosine squared plus the sine squared is equal to 1. The other two Pythagorean identities and forms can be derived from the cosine squared plus sine squared equals 1. So for example, if you start with the cosine squared plus sine squared is equal to 1, and then divide both sides by the cosine squared, that means we divide each term by the cosine squared. Then we end up with cosine squared divided by cosine squared, which is 1, plus sine squared divided by the cosine squared is the tangent squared, is equal to 1 divided by cosine squared is the secant squared. So the 1 plus tangent squared equals secant squared is derived from the original Pythagorean identity. We could do the same thing to derive the third identity by dividing both sides by sine squared. So identities are basically formulas that are true. We've also looked at the even-odd identities. If you're rotating any of the 6 trig functions, if you're rotating the angle in the negative direction, then if it's cosine, it's the same as rotating the angle in the positive direction. Same with secant. But if you rotate sine and angle, the sine, tangent, cotangent, and cosecant, if you rotate negative, then the sine, tangent, cotangent, and secant trig function is negative. We've looked at the reciprocal identities, and we've also looked at quotient identities. Tangent is sine divided by cosine, and cotangent is cosine divided by sine. So what we do in this section is we verify that a trig identity is true, or we simplify an expression using trig identities. So here's some examples. How do we verify a trig identity is true? We use algebraic properties like factoring, adding fractions, simplifying fractions, etc., and substitute other identities to make the left and right hand side of an identity the same. So if you want to verify a trig identity that the left and the right hand side are the same, then you start with usually the more complicated side. We want to show that the tangent theta times the cosine is equal to the sine. So what we can do, we don't want to take anything back and forth across the equal sign. We want to work with one side and make it look like the other side. So rewrite tangent using an identity and rewrite it in terms of sines and cosines. So the tangent is the sine divided by the cosine times the cosine. And what we're trying to do is get the left-hand side to look like the sine. Cosine over 1, the cosines cancel, and I get sine is equal to sine. So I verified the identity by making one side look like the other side. So how do you know if you're starting with an identity, and how do you know it's true? What you could do is you could show using a calculator, if you were to graph each side, your graph should coincide. That means be exactly the same. So if we have tangent times the cosine of an angle, if I graph y is equal to tangent times the cosine of an angle, let me go ahead and write that a little bit better. Tangent of an angle times the cosine of an angle. There's the graph of tangent times cosine. And the right-hand side is y is equal to the sine of the angle. Notice those two graphs are coincide with each other. That means that tangent times the cosine does equal the sine. All right, let's look at another identity using the even-odd identities. Verify the following equivalency using even-odd, that 1 plus the sine of x times 1 plus the sine of negative x is equal to the cosine squared. So we're going to start with the left-hand side and substitute a value in for sine negative x. So go to your list of identities. The sine of negative angle is equal to the negative sine of that angle. So we're going to substitute that in. So I get 1 plus the sine of x times 1. Sine negative x is negative sine x. So I'm going to get 1 plus negative sine x, or 1 minus sine x, is equal to the cosine squared x. Keep working with the left-hand side. All of the algebraic manipulations work with trig functions. So we take 1 times 1, first, outer, minus the sine x, inner, plus the sine x, last. Positive sine times negative sine is a negative sine squared. On the left-hand side, the middle terms cancel, and I'm left with 1 minus the sine squared x equals the cosine squared x. Oops, mixing my x's and my thetas. We make sure that you keep the same variable. But 1 minus the sine squared of x is the cosine squared. And what we used is the Pythagorean identity. Sine squared plus cosine squared is equal to 1. Any variation of that is also an identity. The cosine squared is equal to 1 minus the sine squared, or the sine squared is equal to 1 minus the cosine squared. So any variation of that Pythagorean identity will work. So we proved the identity, or we verified that one side was equal to the other. Next example, we're going to verify another trig identity involving the secant squared. We're starting with the left-hand side. Secant squared minus 1 is divided by the secant squared is equal to the sine squared. So there's a couple of different ways that we can do this. You can take a look at your Pythagorean identities up top. So secant squared minus 1. Up here, secant squared, if we subtracted 1, would equal the tangent squared. So secant squared minus 1 is equal to the tangent squared. So we could have tangent squared substitutes the numerator over the secant squared. And we want to show that that equals the sine squared. Well, we can rewrite tangent and secant in terms of sine. So next step would be to write tangent. You could write that as sine squared over the cosine squared divided by secant squared. Secant squared is 1 divided by the cosine squared. And if you think about these fractions in a couple of different ways, if you have a complex fraction, you can multiply the numerator and the denominator by the common denominator of all fractions. That means I can multiply the numerator and the denominator by cosine squared because it's the common denominator of each fraction. And what I end up with is sine squared over, the cosines cancel each other out, over 1, which equals the sine squared. So I've just proven that identity. Another way you could do that is you could have also, option 2, you could have rewritten secant squared minus 1 over secant squared as 2 fractions. You could have written that as secant squared theta over secant squared theta minus 1 over secant squared theta. And if we did that, the secant would end up being a 1 minus 1 divided by the secant squared is the cosine squared. 1 minus cosine squared is the sine squared. So there's actually two different ways you could use the algebra manipulation and the trig identities to show that the left-hand side equals the right-hand side. All right, some of the homework problems ask you to simplify the identity by rewriting either as a single trig function or to simplify and write it. It doesn't have a right-hand side equal to the left-hand side. It'll just have one side. So if we have simplify and write the trig expression as a single trig function, one of the hints is to rewrite it in terms of all sines and cosines and then simplify. So if we have 1 plus the cosine over 1 plus the secant, then we can rewrite that as 1 plus the cosine over 1 plus the secant is 1 divided by the cosine. Now I've got an expression with complex fractions. The common denominator is the cosine y. So we can multiply the numerator and the denominator by the cosine y to simplify the fraction. In the numerator, multiply, I'm just going to leave it written as cosine y times 1 plus cosine y. And then in the denominator, I get 1 times cosine y is cosine y plus 1 over the cosine times the cosine is 1. It ends up that the denominator can cancel with the numerator, and I'm left with the cosine y. So to write that as a single trig function would be cosine of y. So let's look at another example to simplify and see if we can do the same thing and rewrite it as a single trig function or get it as simplified as possible. So we rewrite, we have cotangent, cosecant, and sine. Rewrite each in terms of sine and cosine. So the cotangent is the cosine divided by the sine over cosecant, which is 1 over the sine, minus the sine. The common denominator for all of the fractions in this complex fraction is the sine t. So multiply the numerator and the denominator by the sine. In the numerator, the sines cancel and we're left with just cosine in the numerator. In the denominator, 1 over sine times the sine is 1, minus sine times sine is the sine squared. But the sine 1 minus the sine squared is the cosine squared. So that gives us the cosine t over cosine squared t. Well, we can cancel a cosine with a cosine on the bottom, and we get 1 over cosine t, which can be written and simplified one more time. 1 divided by the cosine is the secant. So this expression, cotangent over cosecant minus the sine, can be written and simplified into just the secant.